In order for us to understand about chemical equilibrium, we're going to actually have to unlearn a couple of things. So what we're going to do is we're going to go way back when you first learned about the differences between chemical change and physical change, and we're going to have to revisit that so that we can unlearn some important, unlearn a thing that's going to cause us a problem. You, at one point, learned that physical changes were reversible and that chemical changes were not, and that was how you told the difference between whether or not something was a chemical change or physical change. We have to unlearn those two statements.
Aww.
I know, but that's where we're at. So if we start with physical changes, you would have learned that ice, solid water, can be melted and turned into liquid water, which can then evaporate into gaseous water, and off it goes. And we could actually write that down in some sort of chemical process, more of a physical process, but using reaction type language and notation, that the solid melts to the liquid, which evaporates to the gas. However, we also know, and this is one of our key features about a chemical change, was that gaseous water can recondense into liquid, which can fall down as rain, and then we can, if we get it cold enough, we can turn the liquid into a solid. And we can do those processes back and forth multiple times, and that was how we knew what a physical change was compared to a chemical change. However, what we need to do, and the reason why we have, our experience doesn't really challenge that notion, especially this notion here that all physical changes and all chemical changes are reversible. The reason for that is that we are accustomed to what's called an open system. Now, if we think about an open system as a bottle of water, don't judge my artwork, although it is pretty bad, and we put water in there, and we have the lid off. That's that other little hole there. Now, we know that the water is going to evaporate. Now, it's possible that some of the gaseous water will recondense and that be droplets of water on the inside of the container or something like that. But really what's going to be happening, because that lid is open and the system is open, is that we're going to have water vapor escaping through the opening, which will mean the overall water content in the bottle will decrease and eventually will dry out altogether. If, however, we had a closed system, now the story is a little bit different. We put our water in the closed system, and I'm not really sure how it got in there because there's no opening, but we'll make it happen. If we put water in there as now a closed system, that water is going to evaporate. Some of it will evaporate into the gaseous state, and then what will happen is the gaseous water will recondense into the liquid. However, you're going to have an equilibrium setup, so at certain points, as more water might evaporate from the liquid into the gas, some of that gaseous water will then recondense back into the liquid form. And then we could write the arrows going both directions like this. So as liquid water is transforming into gas water is transforming into liquid. And it'll happen so that it's happening at the same rate. So as more liquid is evaporating, more gas is condensing. It'll never hit the point where there's equal amounts, equal masses, but equal rates, and that's what's important. So in a closed system, there's no transfer of mass, and that's key. Now, you could have a open top beaker as a closed system as long as there was no gas involved. So if everything stayed in solution or some solid was involved, then you don't necessarily have to have a closed lid in order to have a closed system, as long as you have no transfer of mass. If you look at a water bottle, now I didn't have to draw that, but if you look at a water bottle that has a closed lid and some of the water has evaporated, you'll notice that some of that gas must have recondensed on the sides, and that's why you get these tiny little droplets. It's not that somebody shook it up and the water from the water state landed on the sides. Some of that gas stuck to the sides recondensed. Now, you've probably seen things like this happening in situations where there is a little bit more of a temperature dependence. However, questions that we're going to need to be able to work with, and you don't need to write these down, but questions that would follow from this idea of an equilibrium setup where gas is going to liquid, liquid is going to a gas, how much water would actually be able to evaporate? How much could I get in the gas state? And how much would then recondense? So would I just have a few droplets on the side? Would I have a lot of droplets on the side? If I knocked all those droplets off the side, would I get more back? How long would that take? If I put it in the fridge, would that change the situation? If I put it in the sun, would that change the situation? And if you're like me, I've seen bottles of water that look like that more when they've been sitting out half consumed on a sunny day. So temperature must play a role. Now, we're going to look at equilibrium as a couple of definitions, so these are important. And then we're going to look at a chemical system, at least in a more of a artistic fashion. Equilibrium is said to be the point at which the forward rate of reaction is equal to the reverse rate of reaction. So now that we understand about rates, we can talk about equilibrium, because equilibrium is about the rates of reaction. The reaction will seem to have stopped. So, based on everything that we can see, if we have a reaction that's happening and stopped happening, we might look at that and say it's finished, and nothing is going on anymore. But once we understand about equilibrium, we'll see that there's actually a lot going on, that there is reaction going forward and there's a reaction going reverse. So in that sense, it's a bit of a balance point. However, it's not a balance point with mass. So it's not that there's equal amounts of reactants and equal amounts of products. It's equal rates of producing products versus reproducing reactants. We then call it a dynamic equilibrium. So for us, whenever we say equilibrium, we'll intend it to be dynamic equilibrium rather than running around making sure that we say both words each time. But dynamic means something is happening. Equilibrium means a balance point. Sometimes you'll hear the analogy of it's like a duck where it doesn't seem to be moving, but the legs are swimming along a lot, so there's a lot of things going on, it just doesn't appear to be happening. So to represent an equilibrium then, we're going to use a double-headed arrow. Now I'll use sort of rather than 2 points or 2 pointy things on my arrow, I'll use that. And what you'll see there is the reactants form the products can form reactants. We're not going to get worried about terminology in terms of the words reactants and products. We'll still use them as they are left to right. The extent of the reaction, we're going to use this idea of an equilibrium constant, or Kc. Now I'll sometimes just use it K, but that is the concentration of the products divided by the concentration of the reactants, where those square brackets mean concentration, which is typically moles per liter. Okay, now if I have a number for that, and I've got the concentration of reactants over the products, and I look at the number, if that number is larger than 1, that means there's more stuff on top, more products, less stuff on the bottom. Products are favored. If it's less than 1, there's more stuff on the bottom, more reactants than there are products, and that means the reactants are favored. And if it's about 1, and whatever those mean, about and bigger than and less than, then it means that they are roughly about the same amounts. Okay, how do I know K? Well, I need to have equilibrium concentrations. If I know a reaction, and I've got my general reaction here with balancing numbers, then the value of K, this equilibrium expression, becomes this, okay, where the balancing coefficients become exponents. And I need to have equilibrium concentrations. Now, equilibrium constant, and then beside that is equilibrium expression, just to hear different terminology that's going to be used. If I have a reaction, so I've got this one, and I'm going to represent the hydrogen as green circles and the iodine as yellow circles, and of course they're diatomic, and the hydrogen and iodide as, well, a combination. What's going to happen is I have my closed system again. I put in some hydrogen. I'll put in an equal amount of iodine. Some of the hydrogen will react with iodine to produce hydrogen iodide. If I now have, and it just happens to work out that I've got a 1 liter container there, but if I now have that system at equilibrium, then I now have, count them up, 5 moles per liter of hydrogen, 5 moles per liter of iodine, and 2 moles per liter of hydrogen iodide. I take those values and I put them into my equilibrium expression, which is based on the reaction, and I get an equilibrium constant. Now, I'm not saying that that's the exact equilibrium constant for that reaction all the time, just for this particular time. And you can see it's a smaller value, so it favors the reactants rather. Now, true, what if? Because I will typically know what concentrations I start with. And if I have a way to determine the concentrations at any given moment, I won't know for sure if they are at equilibrium. So what do? I find what's called the reaction quotient. Now, the reaction quotient looks suspiciously like the equilibrium expression. And mathematically, you find it the same way. The difference is that with the equilibrium expression, the equilibrium constant rather, those concentrations are at equilibrium. And if I'm not at equilibrium, then I call it the reaction quotient. So if my reaction quotient equals the equilibrium constant, then I'm at equilibrium. If it doesn't, well, then is it too big or too small? Well, if Q is bigger than it's supposed to be, that means more stuff on top, less stuff on the bottom. Reactants are favored. That means the equilibrium will shift to form reactants. If QC is too small, then not enough stuff on top and too much on the bottom, then that means the products are favored. That means the reaction will continue to produce products until the right amount is on top. Okay, whirlwind tour. What's really important for us to understand right now is how to come up with the equilibrium expression, that Kc equals all that other stuff, and how to decide if you are given concentrations, whether or not that system is at equilibrium or not. From there, we'll do a bunch of stuff to figure out how do you calculate what the concentration should be, what if I know K, what if I don't, all this. So we'll do a lot with equilibrium. It's going to take us a couple of weeks to get through it all, but we've got a good starting point for now. We'll talk to you in class.